Okay, I think we should start. Good afternoon, everybody. We have a great honor to have Professor Józef Spałek from Jagiellonian University at our today's talk, which begins our new semester. And he will be talking about his and his collaborator works on high TC superconductivity theory. Józef, please start.
Okay, thank you very much, Oleg, for inviting me again. This is my third time in the last 2 years when I'm speaking to your seminar. And so this is kind of summary. As you can see, I have entitled my talk, Theory of High Temperature Superconductivity, but of course with this strong underlying condition based on strong correlations. And what I concentrate on today is quantitative comparison with experiment. Just to tell you where we really are, particularly to experimenters. I will just close the door. Okay. So the meeting in progress. Okay. These are my collaborators, Danuta Gocjago, who he operated here, and you will see her name on some of the papers, and Maciek Fidrysiak, who was concentrating the last year. She came from Technical University, from Politechnika Wrocławska, is here with us as now assistant and finishing his habilitation. This is Michał Zegrodnik from AGH, from Academic Center of Materials and Nanotechnology at AGH. He already habilitated and is professor of AGH. The next one down in the bottom is Andrzej Biborski, who is finishing also his habilitation, is also at admin at AGH. And the two last names are the Jan Kaczmarczyk, who was actually the first PhD student who started this our micro revolution in high temperature superconductivity. He is now working in private biotech company. He has its own part and it's all these private firms. And the last one is Marcin Abram, who is now in California. He married an American sociologist and they are living in California, and he's teaching at the college, informatics and physics. So as you can see, there were other people which were my students during the last 10 or 9 years, but I'm only showing those who cooperated with me or who worked on the subject of the talk today. The plan of my talk is as follows. Oops. First of all, we see that. I have to. Yes. Well, we are talking about high temperature superconductivity in very brief perspective. Then I will talk about 1 and 3 band models for the cuprates or of cuprates. And the main message from theory point of view is that we are going systematically beyond the mean field approach. And of course, therefore, only then we are able to compare the results quantitatively with experiment. And then the second part of my talk is the work of mainly Maciek Fidrysiak. We published 3 or 4 papers together in the last 2 years about quantum fluctuations. Actually, these are collective spin, paramagnons, and charge plasmons excitations in those systems without long-range order. So you have collective excitation, spin, paramagnons, not magnons, but paramagnons, and plasmons, which are always there. But we had to extend our approach. And then I'll provide you at the end a brief outlook, and among them I will list at least 2 topics which have not been tackled so far and provide the reasons why they were not tackled properly. Okay, these are 2 main people who played a very important role in my life. First one is John Hubbard, whom I met when I was a postdoc in 1980. I was a young postdoc at Imperial College in London. Of course, he's his cigar in his hand. He died, unfortunately, when he was 50, not yet completely 50. And the 3.5-hour discussion with him when he came from California. He left England a few years before, and the 3.5-hour discussion with him changed my life. And the second one is, of course, Philip Anderson, who actually pointed what is the crucial fundamental thing in this high TC superconductor pairing. Mainly, this is the so-called real space pairing. I had the all model derived 10 years ago, and for my ignorance was, or our ignorance, because I also worked with other people, ignorance was that we saw only spins on this model, but not Cooper pairs in real space. And so that's how it is. Okay, so that's the first paper which I have started immediately after I learned about the real space pairing. I had all the models. As you can see, the Hamiltonian is quite complicated Hamiltonian. This is one of two formulas which I showed today, and you have spin-spin interaction, but the difference with Anderson was that here there are moving spins, and this is represented by hopping of the so-called projected fermions. So there are moving spins, and out of that, I have created an exact transformation proposed. This is the second part of this paper. I proposed the pairs, and then immediately it turned out that the pairing is possible in this new representation, not is very complicated fermion spin representation, as you can see. Okay, now the talk today is based on the review article which we have submitted, where we've been I have been invited 2 years ago. Unfortunately, it took 2 years to finish it, and it contains 1 over fine structure constant pages. So who knows what fine structure constant is, knows how many pages it has. Probably, I should say, 137 pages so far. Probably in the technical revision, which we still have to make, we'll add certain things. And all the formulas, something 500, 400 formulas are in this paper. So today I will be talking about the results, not on the formulas, because this would require complication to the talk, additional complications to the talk. And but so who is interested, then I can send easily the paper, because I presume that this paper will get published in 3 to 6 months. Okay, then fundamental thing, of course, is, as most of you know, this fundamental discovery was that we start from the Mott insulator, which is antiferromagnetic, and then we dope it with holes. So originally we have 1 electron on the x square minus y square orbital for copper 2+ ion, and then kick out part of the electrons and replace it with holes. And when you create those holes, those spins which were blocked in Mott antiferromagnetic insulator start moving, and believe it or not, it becomes superconducting, and it becomes even high temperature superconducting. And as you know, it can be easily reached 94 Kelvin. Of course, there are systems with higher TC, but let's say it's 91 or 94 Kelvin, which means above the liquid nitrogen temperature. And if you don't know, I just would like to tell you one very, very important thing. A week ago, maybe 10 days ago, I read in a newspaper that at MIT they have tokamak. They try to produce this so-called thermonuclear nuclear synthesis in small reactor tokamak, and the magnets which were used, they were stripes of high temperature superconductivity. And the breakthrough came with this increased field, critical field for this high temperature superconductivity. And they kept this plasma for quite some time, which means matter of 10 or 20 seconds, stable with 0 production of energy. So it seems breakthrough is coming, maybe not in this at this time, but maybe in 1 generation of producing the electric energy. And then, of course, on the right, I have our first paper on this new revolution, which we have called here that we have produced first statistically consistent mean field approximation of the superconductivity. And forget about antiferromagnetism. We've been interested only in superconductivity. And then you can see there is this beautiful dome-like behavior, because the fundamental question was, once the system, you dope the system with holes, so you create more and more carriers, correlated but still carriers. And the system becomes better and better metal, and then better and better metal. And then if it's a good metal, which is Fermi liquid, the superconductivity disappears. This I immediately realized, probably with many other people as well, that this must be not typical superconductivity. In the good metallic phase, the superconductivity disappears. And the hypothesis was the holes dilute those correlated spins, which somewhat are related to Cooper pairs in real space, because antiferromagnetically coupled spins, it's the same as local, you can say, Cooper-like pairs in spin singlet state, of course, in real space. And this is this most elaborate mean field theory you can imagine. And you can see that this upper critical concentration is about right. Here in real system on experimental sites, it's 1/3, 1/4. And here it turns out when you change the parameters, about which I will be still talking later, you can almost move the system correctly to experiment. And but on the left side, where you have antiferromagnetism, superconductivity disappears only in the Mott insulator limit. If antiferromagnetism joins in, then it suppresses superconducting phase on the Mott insulating side for low carrier concentration. So these are the main first qualitative features one has to reproduce in order to describe this novel type of system globally. Okay, now I jump by 10 years. And this is the results which we have produced with Michał Zagrodnik in 2018. And then what we see that this phase diagram, which I was showing, is much more complicated. And this, on the left, experimental result is taken from the PhD thesis by Biało from AGH and the Technische Universität Wien, which I am actually referee of, and I put this picture just today, an hour before the seminar. And you can see that you have this beautiful dome, as usually, but on the so-called underdoped side, when the TC goes down towards when you move towards the Mott insulating phase, a new phases appear. The first one is the so-called pseudo gap, which you can see in electronic states. And Henri Alloul was the first one who discovered that, the French physicist, with the help of nuclear magnetic resonance. And then, of course, later people have shown that there is this charge density wave state, and these are the experimental points of this PhD student, Iza Biało, Wojtek Tabiś, and people from TU Wien. And you can see that this beautiful charge density wave state appears, or charge density wave state. And you can say, well, here TC for this charge, or what happens like critical temperature for charge order is higher than the superconducting true temperature, which is this lower blue or violet curve. Whereas here in your theory, we have only T equals 0 here results. So this is value of the gap for the charge density wave, and value of the gap, correlated gap for the superconducting phase, whereas the charge density wave gap should be smaller than the superconducting gap magnitude. So how come the TC is higher for charge density wave than for superconductivity? And of course, after a minute of reflection, you realize that the charge density wave state is the so-called diagonal ordering, that the temperature of ordering is proportional to the order parameter proportional to the coupling constant. So it's linear, at least in the mean field or mean field light approximation. Whereas for superconductivity, the Curie temperature or the critical temperature is exponential function, at least in BCS theory, where in interaction in coupling parameter. And this exponential dependence kills this. However big this here, bigger this delta is, kills the TC becomes lower. Okay, so you can understand it qualitatively, at least, because quantitatively, we still haven't calculated the whole thermodynamics when we go beyond the mean field. Within mean field, you can calculate it, and TC, theoretically, TC is about 2.5, 3 times too big than the experimental value. Okay, now we come to the model. Just only one phenomenon, or just one phenomenon, which is the phase diagram, and immediately I jump to the model. So, as you know, the cuprates, at least, they are composed of planes, copper, oxygen planes. Let's say that this copper oxygen plane, and this is the stack of planes. Forget about chains, forget about many plates, but it's periodically stacked copper oxygen planes. And there you have on a single plane, you have just moving spins, moving electrons. Of course, they are correlated, but since they repel very strongly, so essentially they are moving only through on the empty states. Of course, those here, those deep well states, these are periodic potential, but they move, for example, from here to here when there is no electron, so they can move quickly, because if it encounters another electron with opposite spin on its way, they are repelled, and so they jump in and jump out. They only undergo virtual transition back and forth. Okay, and the model which we have invented, which is generalization of our original TJ model, or the original Hubbard model, which we called Hubbard TJU model, and the paper was published in 2017, so let's say 4 years ago. And you have the first 2 terms is the so-called Hubbard model, which means that you have written kinetic energy is somewhat second quantization as the jumps, as the hops between the sites. And when they encounter 2 in number of electrons, they spin up and down on the same site I is 1 and 1, then the U intervenes, huge, the largest energy in the system of the 10 volts, 10 volts, 10, 12 volts, even between 8 and 12 electron volts, whereas this TIJ, this whole copying magnitude, is fraction of a volt, electron volt, 1/3, 0.35. So the bare bandwidth without correlation is of the order of 2.8, 3 electron volts. So here you have total kinetic energy, which is half of the bandwidth, which is something like 1.5 volt when it's not renormalized. Here you have 10 volts, and then you have intersite interaction, intersite direct Coulomb interaction, VIJ, which is about 1/3 of U, let's say this 3 volts, 3 electron volts, and then you have this J, this antiferromagnetic interaction with positive JIJ, and this is of the order of 0.1 electron volt. And so J value of nearest neighbors antiferromagnetic exchange integral is of the order 1300, between, let's say, between 1200 and 1500 Kelvin, which is 0.1 electron volt. This is small on the scale of those of the remaining quantity parameters here, but it's a record holder for the magnetic system. It's really huge interaction in this strange 2-dimensional copper-oxygen plane, the copper-copper coupling via the oxygen. Okay, and of course that was what I was showing, got one band model with corresponding 2-dimensional Brillouin zone with ordinary notation of the high symmetry points. And then you have free, moralizing is free orbital model, which is you have here this 9th electron of copper, which interests us because all the 8 electrons down by something like 1.5 electron below those level of the 9 electrons. So it's the orbital is, as you can see, dx square minus y square orbital. And then you have this in anti-bonding because it's 9 electrons. So to feel completely the shell, it's only 1 electron is missing. So this is the anti-bonding notation with respect to the notation of the orbitals and signs. And here are the corresponding hopping between p orbital, py and px orbital. There's dp, the hybridization of the p and d orbitals. And then, of course, you don't have direct, you assumed you don't have direct d orbital hopping because the orbitals are somewhat restricted because these are correlated orbitals. But of course, the effective d hopping in one-band model comes from hybridization because electrons, these 9 electrons, hops to this and then hops further if the p shell is not complete. If you do tight binding theory with those three types of orbitals without u, without j, without v, anything, then of course, as you have 3 orbitals, you expect, as in hydrogen molecule or any, you have 3 bands. The lowest one is the bonding band. The one in molecules, this would be 0 energy point, as this non-bonding band, and then it's anti-bonding band. And now, if you have 2 electrons on one p band, 1 p electron, 2 electrons on another p orbital, px, py, so it's 4 electrons, and this 5th, which means 9th electrons, is here have filled band, anti-bonding band. So this bare band structure, of course, is not correct because the system is a Mott insulator, spins are localized. In other words, this band, this anti-bonding red bands is reduced to 0 to a level. And that's the reference point, which you may say it's chemical potential position for the Mott insulators. And then once you create holes either in P or in D, though here they are not exactly 1 electron half-filled band, and these bands becomes active. And we'll compare the results between 3 orbital model and with 1 band orbital within 3 band orbitals, but 1 band orbital, 1 band system as well separately. Okay, so that was the starting point. And here I have put here the model which I always show, very crude model. Oops. Okay, so you suppose, let's put back. So suppose you have this antiferromagnetic Mott insulator lattice on the copper ions Cu2+. These 9 electrons are ordered antiferromagnetically because they are strongly coupled. There are no bends, there are only level. Exchange interaction survives going when there are no holes, survives because it corresponds to virtual hopping processes. Just a moment, there is something wrong going on in here. So you can see, but if you have 1 electron and it moves to the whole system, suppose we have 2 holes. You see this system, this state, this moving of electrons from left to right is very inconvenient energetically, because here, if there are no holes, you have beautiful antiferromagnetic arrangement to sublattice arrangement of A-type, as we say, symmetry argument. But if it moves, this is inconvenient energetically. So what spin does? It rather prefers do double hopping, and then again is recovered. This antiferromagnetic structure plus those 2 holes extra is recovered, so energy is lower. But then, if one moves, it breaks the bond with the other electrons neighboring, which is exchange coupled, strongly coupled. So what they do? They move, and one drags by 2 and drags the other, drags behind the other because of this. And therefore, they move in pairs. One goes, then second follows, and so on. And effectively, the whole moves from the configuration above to the configuration below. And that's the essential feature, one of the essential feature of this spading mechanism. But it's only the part connected with exchange coupling, and still it's not an exact expression, because here I put antiferromagnetic lattice, whereas in actual superconductors you have paramagnetic lattice. So therefore you have spin ups and these part intermixed in the more or less random way, but still the rest is done by the so-called correlations, by this large U. And how does it do? That's the heart of the problem. That's the heart of the problem. Okay, now so we did this in mean field approximation. As you know, the two upper slides I have already shown. And then, of course, the surprise was the not so nice surprise that when Fermi velocity of those holes have been measured versus doping, here you have number of holes per copper atom, and at the right lower panel, and you can see experimental points for lanthanum, for 1, 2, 3, for bismuth compounds. They are practically independent. Fermi velocity is independent of concentration of carriers. This is stupid from the point of view of ordinary Fermi liquids and metals or semiconductors. Because if you change the number of carriers, the Fermi velocity should be smaller and smaller, because Fermi surface gets smaller and smaller. And these are the Fermi velocity in this lower the continuous curves in this lower right hand panel. You can see that the mean field, the most sophisticated mean field, does not reflect the experimental dependence, fundamental concentration independence of Fermi velocity. And this is one of the big puzzles. So even though you can explain this dome-like behavior, you cannot explain the single particle dynamics. And of course, since you have Fermi velocity, you have only in the so-called diagonal case, because superconducting gap is only along the gamma m direction 0. So then fermions can propagate easily without gap in the so-called nodal direction, when kx is equal to k1, and this Fermi velocity was measured then. But then in the anti-nodal direction, where you have full gap, you can see that this gap also is, the trend is okay, but it's still not quantitative at all, because however you change the parameters from the curves 1 to 7, whether you change V or change U or change J, you cannot recover correctly the tendency. So that's the failure of the renormalized mean field theory in our version, which is called statistically consistent Gutzwiller approximation. And that was 2011. And then we move 6 years later to the paper 2017, the 3 papers 2017. And then what we discovered, here are those points for Fermi velocity in nodal direction as a function of doping, delta now, not x, but delta, it's the same. And you can see it's almost constant. And you can see here that, that you can see that average velocity is 191, which we have, but of course it varies slightly depending on parameters, but essentially we recover for reasonable value of parameters within the 5 of 2%, 3% accuracy, the average or universal Fermi velocity in this system. And then the test was to take those parameters from fitting this very not obvious curve in upper right-hand corner, take the same parameters and try to test whether other physical properties, experimental, will be reproduced quantitatively. And now I move to the left-hand upper corner, and then I move to the to the paper by Deutscher and co-workers. In 2005, they produced the first results. Here, I essentially reproduce main papers, not the newest paper, but there are not so many measurements. And what he did, Deutscher with his friends, with his co-workers, is that they measured the so-called non-BCS behavior. What you have here on the y-axis is the change of kinetic energy in the superconducting state with respect to the normal state, paramagnetic metallic state. Okay, they can measure it by optic conductivity and van Kramer's chronic relations, but please don't ask me about the experimental details, because simply I don't know it. So here you have change of kinetic energy superconducting phase in milli-electron volts per copper ion. And here you have relative doping, which means you take the actual doping and subtract from it the optimal doping, which is in this case something like 0.15, 15% of number of holes, it's the optical doping. Sometimes it's 17, sometimes 13, in some system comes to 0.2, but it's always within 10, 15%. In all the cuprates is the same, it's essentially the same. So you can see that at low doping, which means below delta minus delta optimal is negative, there is a loss of kinetic energy due to pairing in superconducting phase with respect to the paramagnetic phase. But then when doping goes higher than the optimal doping, which means we go to the overdoped regime, it agrees very well with experiment. He then with this original data, there were only 5 points. And that's what we had when we were fitting the data. But what was very interesting was with the same parameters, our previous TJ model does not reproduce the system. Or you can the earlier even full statistically consistent Gutzwiller approximation does not reproduce correctly the trend of the data. That you can only BCS type of behavior, because in BCS model, you have just potential energy gain, because due to the onset of superconductivity, what changes in the electronic spectrum is that gap opens up at Fermi energy. So the field part of the spectrum gets pushed down by delta, and the empty states are pushed upwards by the amount of delta. And so therefore you have change only in potential energy, not in kinetic energy. And therefore, if there should be only positive. And here we can see, so that was actually, I would say, the breaking point for us, that this theory, which contains going beyond mean field, 1,000, if not more than 100,000 diagrams to go from the deviation from the saddle point approximation, which means mean field theory, and include further correlations when intraatomic one, that the electrons correlate at certain distance between first, second, third. And if you go beyond correlations between third neighbors, fourth, fifth, the results are rapidly convergent. So it means you have an asymptotic expansion of this of the energy of the system and the wave function of the system, but it's rapidly, well, not so rapidly, because every one order higher involves order of magnitude more, well, not order, but it's a lot of more computations. Then we said, so let's see, the Fermi wave vector was measured. I am now going to the lower panel, lower left-hand corner panel, and they measured Fermi wave vector versus doping. And points are for lanthanum strontium copper system, and this is taken from the papers Carbon and the later paper by Kordiuk and Borisenko. And here it's the dashed curve is mean field theory, which means it reproduces very well. And there is this correlation included going beyond the statistical mean field, so that's fine. Looks, it goes, the trend is the proper one, but there is not so much to test, even with the same type of parameter. All these for the same amount of magnitude of parameters. GWF is Gutzwiller wave function. LSGA is statistic consistent Gutzwiller approximation. LSTO is lambda 2 strontium 2 minus X, strontium X, copper, oxygen 4, right? And J, you can see, is here in units of T. So this means 1/4 of T, which means 0.1, 0.12 electron volts. And this is also U in units of T. So it's one, if you divide it by 3, so so it's 7.5 electron volts. And everywhere the parameters are the same. And then the last one was the effective mass enhancement. And this was a big surprise, at least to me, not to my coworkers, because they are much younger. Because, of course, always when we talk about strong correlation, we immediately say masses must be heavy. Effective masses must be heavy. In heavy fermions, the masses are 1,000, at least 100 mass of free electron. For example, in typical cerium, copper, indium 5 is 100 free electron mass of quasi-particles. But in cerium, aluminum 3 is 1,000 of free electron masses. Here, they are not so large. They are enhanced by factor of 3 or maybe by factor of 4, but not so much enhanced throughout the doping. And then I understood it that it turns out that the effective mass gets enhanced very largely close to doping zero, close to the Mott insulating limit. So you can see in the mean field approximation, this dashed curve again, the mass goes up as doping goes to zero. The mass goes up in very rapidly, which we haven't put here because below 0.05, which means P.O.5% antiferromagnetism is stable. Only under pressure you get stable superconductivity or some other system. And you can see it reflects the trend of experiment, but in lanthanum strontium, the mass is enhancement to the value of 6, which this theory does not reproduce. And then, of course, it's again, there must be something happening, and that's actually this onset of the charge density wave ordering or pair density wave ordering in the underdoping regime. Okay, so these are just the correlated gap. Again, we reproduce here the dashed curves are essentially mean field, and the continuous curves are the correlated, included with those two values parameters of J and so on. And then condensation energy. Look, look, TC is 100 Kelvin. 100 Kelvin, and the condensation energy, gain in energy when system goes to the superconducting phase, it's about that value, because 14 milli-electron volts per ion, 14 milli-electrons is something like 150, 170 Kelvin. So the condensation energy, even though value of U is 20 electron volts, value of T, value of bandwidth is 2 free electron volts. Value of J is 100 milli-electron volts. Value of V is 2 electron volts. The actual condensation energy is in the millivolt range. So you can see how big renormalization and competition between those big energy value takes place in order to reach such a subtle scale of condensation energy. And that's what correlation does. That this value, large value of U, suppresses the motion of electrons. It reduces T, but by the same token, T moving reduce U, and U again reduces J, and so on. And they reduce, and those renormalization factors are analytic, but they are quite complicated formula. So if somebody wants really to see what it is, it must go to the physics report, must go to this physics reports preprint, and of course I will be happy to send, because critics is always good. I am even happier if somebody writes something critical.
Excuse me,
Yes,
can you, okay, on this lower right picture, this mark
Yes.
P, what is the difference between the red and dashed black curve?
Yes, these are, you see, they are different parameters because as you can see that those inverted triangles, they correspond to the lanthanum strontium, whereas the green corresponds to IPCO. It's a, I would say it's a small, you see, this is the full theory, this red line. This is full theory.
Then you do not get that divergence at zero.
Because we don't know what is. Maybe not. We unfortunately, that's a very good point you made, Oleg. It turns out that our theory, unfortunately, it's very difficult to get beyond mean field if you include correlations, particularly beyond, in particular when you go beyond third of higher orders. We essentially here, as you can see, this curve does not go to actually to delta zero. Also, mean field doesn't not go exactly to delta zero because the results that do not converge numerically. You see, these are usually system of 6, 7 nonlinear integral equations with sometimes with singularities, even in the nucleus of the in the kernel of the integral. So we cannot go exactly to delta zero. But this doesn't, I hope you agree, this doesn't, how to say, bothers us so much because there is antiferromagnets there. So there is no much harm done. We cannot calculate it with the accuracy at the delta going to zero, for example, equal to one part in 100, something 0.05. All this is less and less accurate, but I would say trend is still okay. But then here we cannot reach, at least on the computers we use, we cannot reach convergence.
But
okay.
The second point is that both blue dots and this triangles corresponds to lanthanum strontium.
Yes, to different authors. Yes, they are different.
The discrepancy is very large.
Yes. One, to tell you the truth, I think I know the difference. The all-day purpose people do not know that such thing like charge density wave or stripes or whatever may appear. Well, stripes, the doping is too big for stripes, but charge density may appear. And those blue are the newer type of newer references. Okay.
And this is all from transport or from optical data?
Again, this guy comes. I think part is from Hall effect. Hall effects, but if you look in the paper by Carbon or by Molegraph, Molegraph is optics, is optical conductivity from the some rules. Carbon, it's I think it's a whole correction to the classical Hall effect. I think Kordiuk and Borisenko, they are more neutron-like guys or scattering-like guys. How do they do it? I don't know. Okay.
Thanks.
Okay, so now it's some kind of summary. This is some kind of summary where you have BCS. So you can see that it's here is as a function of Coulomb repulsion. So U is in units of T. So the actual value of U in electron volts you must divide by 3, approximately 3. So here where U is 35 means it's 12 electron volts. When U is 5, it means this is 1.5 electron volts. So it's in the full possible range from more or less normal metal to extremely correlated system. And doping is as usually, because doping from multi-insulator, when doping by holes is 0 to 1/3. And you can see optimal doping changes with value of U. And this system, those systems, they are the same type of model. But the value of parameters varies. Why they vary? Because they have slightly different structures, and therefore they have slightly different lattice constants, interatomic distances. And this influences the parameters, but not so much. They are in the same, as we say, universality class, but the parameters may change by like, I think the most realistic value is starts with 10 to something like 25. And here you can see that, that this optimal doping, it dips down for something like U equal 8, and then goes levels off when U is in this high TC realistic regime, and you have BCS, non-BCS type of regimes. And you can see that they are for two different values of J equal 0.1 and 0.25. And you can see that more or less this the universal is the same. Superconductivity is always between 0 and 1/3. The interesting things always happen something between 10 and 20 and so on, even though the exchange integral, antiferromagnetic exchange integral changes by something like factor 2.5, right? So that's what we say about some universe, maybe not about universality, but about universal behavior. Of course, you can fill it in with other J's, but you can see how it is. Okay. Then now it's back again. I return now to this charge density wave, and now I will say a little bit more about the theory produced in that paper. And then instead of showing experiment by Iza Biało, Wojtek Tabiś, Neven Barisic, and so on, and others, I will show the early results of Badu. Oh, sorry, because Badu from Nature, and you can see again you have this X-ray from X-ray. So these are not RICs, because RICs is in elastic neutron scattering. Here is elastic neutron scattering. They are more or less the same. And here you have, this is spin density wave. So what they observe not like in latanum strontium that antiferromagnetism and superconductivity are separated. They almost touch each other, but there is some terra incognita in between antiferromagnetic insulating state and superconducting state. But in IPCO, they presumably they overlap antiferromagnetic and superconducting to much lesser extent. And this is lower curve here. I don't remember. It's probably in high field. Iza Biało also observes this as a three-dimensional charge density wave state. And it turns out the most interesting is not just charge density wave state, which is characterized by delta X CDW. Here there are no CDW, which means that charge is periodically modulated with the K 1/3. So it's 0, 1/3, 2/3, 0, 1/3, 2/3, and so on. This is not, it's so-called pair density wave, which was introduced, I think, I don't know who originally introduced it, but I think Patrick Lee first theory did on that something like 5 or 6 years ago. And this is pair density. Pairs have density different as you go along the system, but this you have to, in order to incorporate, you have to do it in the reciprocal space and so on. But at least pair density wave, some sort of full Deferrel type of state, you have to include, and you can see everything, whether it's pair density wave in X direction or whether it's in two directions, always reduces the superconducting temperature and always vanishes at optimal doping. That's I think what is principally correct in our theory, even though the propagator, what we say, propagation vector is not adjusted, not optimized. It's just assumed that it's 1/3, 0, 0. It's wave vector just taken from experiment. So even though this optimization, because this would require inputting another integral, nonlinear integral equation, but I think it's, I would say it's fair enough that we get that far and that we get such a qualitative picture as well. Okay, and now back again. That's the other last thing about the phase diagram. Is the last thing about the phase diagram. As you know, there are electron and hole doped superconductors. On the left side, this lower panel, this is electron doped superconductors. On the right-hand side, they are the hole doped superconductors. And here this K value is the so-called correlated hopping term, which Jorge Hirsch introduced that this would be the mechanism of superconductivity in high TC superconductivity. It turns out if you go beyond mean field, this parameter of correlated hopping, it does not influence much superconductivity. Really, correlations plus exchange is the thing, because these are these main curves. And whereas this difference is, as you can see, smaller, actually this K value, if it's worth for what? It's worth, and the intersite Coulomb interaction, that the critical, upper critical concentration for disappearance of super is not 0.42, which is wrong, but it's closer to 0.3 or even lower, depending how big is intersite Coulomb interaction or correlated hopping term. Okay, so that's, and again, you have BCS and non-BCS like borders, and these are the optimal doping for those two curves and so on. Okay, so now finished with now I have the last, let's say 10 or maybe 12 minutes, 15 minutes to tell you what is actually been done recently, which means the last 2 years. As you know, these are two-dimensional metals, and on the left-hand side, as you say, case D, but of course, this is taken from another experimental paper written here. You can see the beautiful open Fermi surface of two-dimensional metal with two hopping integrals, one between the nearest neighbors and the second neighbors, because if there were no second neighbors, hopping it would be just rhombus, would be just like that rhomb, whereas it gets opened, and you can see the beautifully, you can see fit this dispersion relation of the topology of Fermi surface for thallium compound for overdoped samples in this Fermi liquid regime. Whereas if you go to lower concentration, here is again, instead of delta is X, it's 0.1, 10%. It gets broken, this beautiful hyperbola, well, hyperbola-like, only here in the nodal direction, which means that diagonal. This where the superconducting gap is 0, even in normal state is everywhere, but even normal state, here is always metal in superconducting normal state. So only this state survive here, whereas the rest disappeared. So this remaining part, so you can say that the wings of this central spot disappear. And that's the big mystery, which we haven't explained yet. We have the idea how to do that, but we shall see. I will say about at the end about it. I will say about it. Okay, so that's how it is. And now there are those two which are not explained, and what we can say about it, because this is surprising, because we get properly Fermi wave vector fitted in whole doping range, but the details of the topology we do not recover. And this is pretty amazing that you have such things. And then we move to another paper. Here I somewhat parameterize better. And here you have Maciek Fidysiak again. It was his first paper when he came to my group, to our group. That's why he appears for the second time. Sorry, remaining co-authors, but you will not be displayed for the second time. And here is already photoemission spectrum. What is photoemission spectrum? This is intensity of scattered photons, and which this is photoelectric effect. This is kinetic energy of electrons coming from scattering of photons or the absorption of photons, and it's difference between actual energy of electron, which is taken out from its level with respect to the Fermi level, and then this is wave vector, which is momentum with respect to the Fermi momentum. So here you have Fermi level and Fermi momentum, K minus Kf equals 0, and Fermi energy minus, and you can see that it's completely universal, practically universal. This Fermi velocity in this doping, very in full doping range. And that's this That's this velocity, which I already shown within the static approach. Here is the alternative approach in K-space. And again, you can see here already, since this is a later paper, the fitting is even better for lanthanum strontium. But then they observe the very interesting thing, very strange thing, which was regarded as very strange thing. We have a kink, a break in the dispersion rate, as if there was appearing a new Fermi velocity, because if dispersion relation is linear, coefficient of proportionality between wave vector and the energy is Fermi velocity times the Planck constant h dash. And you can, so this is, it's in electron volt angstrom units if you multiply it by Planck constant, this Fermi velocity here, and it's second Fermi velocity. And so surprisingly, from our theory, this break comes in, and it's also beautifully recovered by this our theory, including in higher order correlations. Of course, previously I was showing static properties. This is also static properties, but dynamic in the sense that it describes the electrons moving around. That was one of the first paper about this kink was written by Krzysztof Byczuk from Warsaw University with Dieter Wolhard, where such thing exists. This was paper from 2007, but our paper is much longer, but then we have the full fitting. And then, of course, again, we recovered the Fermi wave vector within this new approach, which is in the same class. They only calculated not in real space averages, but in real space. And the nodal quasi-particle weight, the spectral function, more or less not so well, but at least the trend again is okay. So that's this linear dispersion relation. That's why I talk always always about Fermi velocity as the slope of those curves. Okay, now the last part, which is the dynamic things. This is the work for the last 2 years, and then we unfortunately, in order to describe plasmons, for the first time we have to use 3-dimensional models. But then you would say, well, how come? Here you talk about 2-dimensional model, everything is recovered, even dispersion relation, topology of Fermi surface is reproduced as 2-dimensional type of rhombus or type of 4 hyperbolas, and suddenly you are introducing 3 dimensions. This is 3 dimensions only in one aspect. Coulomb interaction is long range. So we include Hubbard model for single planes, but between the planes, the electrons only speak via long-range part of the Coulomb interaction. And that's essentially the thing. I think the first person who was talking that this long-range Coulomb may be important, one of the first was Anthony Leggett. But of course, here again, we make the quantitative theory. And of course, the Brillouin zone is now anisotropic 3-dimensional with the corresponding symmetry planes. And what do we get? We get, of course, and that's the last paper. That's the last paper. Here we have paramagnons, which means you can see you have doping 16% in lanthanum strontium system, which means it's not, and its temperature is quite high. Here, which is non-superconducting, non-magnetic, but still spin waves, collective spin waves are observed with non-zero damping rate, with non-zero lifetime. So therefore, we are talking not about magnons, but about paramagnons. Of course, magnons are damped also, but they are damped to much less. The half-width is much lower in energy than the energy of the magnons. Here they are comparable, but still we can quantitatively fit the data in the Brillouin zone. Of course, since we plot here the so-called spectral density functions, so the color tells you, white color tells you maximum of the spectral density, and this is the maximum. It essentially reflects the experimental points. And these are 2 experimental papers, very good paper by Peng from PhysRef 2018, and NAG, who also uses for plasmons free differential potential because they have theory and experiment last year. But of course, what we fit within same parameters, both plasmons and magnons, which they cannot do. They have plasmons, all right, but they cannot reproduce magnons. Here is, as you can see, bare energy of the magnons. Here is the effective energy, the so-called, well, I won't define what I mean by effective, by bare, but the unfortunate damping rate is not so well reproduced. And as you can see, near gamma point, experiment shows nothing. In our case, we show that maximum, there is a discrepancy, somewhat discrepancy here in the half-width. Whereas plasmons is three dimensions, they are very well recovered. And you could say, why paramagnets? You have washed out through antiferromagnetism, this antiferromagnetic, this anti-parallel orientation of neighboring spins. But look, if you excite a magnon in magnetic system, what does it mean? Well, it means you reverse one of the spins. So out of singlet of S equals 0, you create a triplet. So it's a singlet triplet magnetic transition. That's the creation of magnon. And that's at the bottom, you can see as if it was just the spin wave, the precession out of phase. And of course it's dumped, which is not explicitly shown, but essentially the thing is the same. And this is the beautiful thing about it is that you can get those paramagnons, even though the damping is so important. And this is done with the so-called resonant inelastic X-ray scattering, new technique of the last decade, practically. The first paper on that technique was 2012, 2013. But here, these are, as you can see, the experimental papers. The experimental papers are the last year, the best papers. Oh, here are even, but for Mott insulator, we can also beautifully fit the data for Heisenberg, for Mott insulator within this theory, but about these details I won't talk about anymore. So we have exactly 60 minutes, so outlook. Strongly correlated electrons comprise the limiting situation of quantum condensed matter with unique thermo and dynamic properties. And 1 and 3 band model, actually I have 3 transparencies on 3 band model, but I decided I have it behind the last slide. If somebody is interested, I can show in 3 band results. They are essentially very similar, but they are also very interesting thing when comparing 3 and 1 band results. 1 and 3 band models of ITC will describe principal properties of cuprates. By this, I mean, principal means that about 30 papers which we have written, and we have worked very strongly to get it quantitative. Why? Why experiment? Because experimentalists, always say, oh, mechanism is not known. At baloney, it's known something, a strongly correlated system. There are many approximate solutions, and our solution is also approximate. So how to select between the different solutions? And we decided that we will try to compare with experiment quantitatively. And this is the first such an attempt in the world literature. And this, I take me for this word. This is the first such, that's the reason why we have written this 140-page review on that. We shall see what the community will say. And then problem to tackle, as you could see, I haven't shown anything about resistivity. Incorporation of quantum fluctuations, which I have shown on the last 2 slides, into the description of single particle properties, linear resistivity, Fermi arcs, transition from Fermi arcs, and the pseudogap. So that's essentially what we have to do. And the last comment is why so many phases appear? Why antiferromagnetic, superconductivity, charge density wave? As Phil Anderson once said, who ordered it? We don't need that many things. We need only this high DC superconductivity. And because there are here many scales which compensate each other, compare that you have electron volts, and on millivolts, this compensation is taking place. They are almost reducing each other to 0, and whichever term dictates, predominates at even on millivolt scale, this phase responsible for, this phase for which this interaction is responsible for appears, the competing processes. And the last thing, you see, we cannot explain, within our theory, we cannot explain supergap. This is supergap from experiment, roughly, and this is supergap which we have, a pseudogap which we have within our theory. We need to include fluctuation to pull this pseudogap down. And that's the main problem. That's one of the main problem for the coming years. And if we are successful here, I can say that all of us can move to somebody else. We haven't maybe not solved the problem, but at least contributed in very non-trivial way. And you can see here once more again how many parameters in free band model you have. They are more or less fixed, but once you fix them, you have to fit all the properties with those five parameters. Oh, sorry. I'm sorry. This is free band model. Oh, that's it. Thank you very much.
Józef, thank you very much indeed. I appreciate very much your talk, and the particular virtue of your talk was that you made it for experimentalists, which is rare among physicists. So
theorists will say he talks, and nobody knows what he talks about because he doesn't show this.
Well, not, but you have a very heterogeneous audience, so that's I appreciate very much. So now the talk is open for questions and comments and discussion, and please just turn your microphone, unmute, and ask your question. Please try not to interfere with other people. So just wait a second and start asking questions. Please go on.
No questions? Everything clear or nothing clear?
Well, hello, Joseph. I listened with, here is Roman Micnas speaking.
Cześć, Roman.
I listened to your talk, really impressive piece of work, and the detailed comparisons with zero temperature results from the experiment. And I have two comments. First is, it concerns the strong correlations and the D-wave nature of the gap.
Yes.
D-wave nature of the gap, in some sense, automatically avoids strong correlations. So that's one comment. So maybe it's not surprising that you need 20 EV and Scalapino needs 4 EV, for example.
Oh, okay.
So that is the first comment. The second one, you mentioned the correlated hopping mechanism.
Yes.
I'd like to remind you that we were before Jorge Hirsch.
Oh, yes. Sorry, Roman. Yes, Roman and Staszek Grobaszkiewicz actually did it before Jorge Hirsch, and I apologize for that. I apologize.
No, it's okay, fine.
Yeah.
I have no, I just, so that's actually, but all this presentation was really highly impressive.
Yes, Roman, now answering your question, number one, that the D comes automatically, D wave type of gap comes out, not automatically avoids strong correlation. It's not quite so, because you can obtain also within our model, of course, for this we did only in this elaborated mean field approximation, also as wave. Extended as wave appears as well. The problem is that it's like in Landau phase transition theory. The system selects which has a lower energy. So it's D wave is not the only solution possible here. That's whether it's natural. That's with that I may agree. Now the additional thing which I had to add, which I did not tell you about, it turns out in higher orders within our approach, we don't not have only D wave. There are also higher harmonics which means, for example, that you know that we have the second, third, fourth harmonic. Unfortunately, with unfortunately, I don't mind whether it just appears. So the D wave is preserved, but the amplitude of those additional higher components, we would say higher frequencies, higher harmonics, is negligible, practically negligible. So with D wave, it's not pure D wave. Only in mean field approximation is pure D wave. If you go beyond mean field, immediately you observe also higher harmonics. Also, I have to admit also one thing which is still bothering us. It turns out if you switch on, if you calculate charge density wave state, unfortunately also very small component, S wave, extended S wave or S wave appears as well. It's very small. It's something like 0.5% of the D wave gap. But then, of course, it's also, this would mean that, the nodal direction, that this gap would show if we really were scaling a fraction of millivolts in the nodal direction at very low temperatures. This is the thing which all the theories, not only ours, but also mean field theory has, that the immediately S wave component, S wave, very small S wave component appears. So that's additional thing. I hope I answered your question.
Yeah.
Now about now there was Scalapino 4 electron volts. The problem is that if you have single band model, then the principal problem, that was why we did actually free band model as well. The principal thing which you have with single band model, where you want to have antiferromagnetic interaction, this TJ-like type of antiferromagnetic interaction, and get it 0.1, 0.12 electron volts, you must assume that U is extremely small. So this comes from this mapping from free band model into single band model. Whereas in free band model, you have realistic U, 8, 10 as the experimentalists observe, and still are getting the similar results as within the single band model, but then in single band model, you have to change U in order to get the same value of exchange constant. But the results, whereas qualitative results, angular dependencies, and so on, is the same. So there is a principal difference with the value of U, with which actually, which is somewhat doubtful whether single band model can take small value of U, because, for example, George Savatsky asked me, Józef, you have very nice this type of thing, but why do you need, this was some years ago when I was doing still mean field theory, but why do you need this small value of U? I say, okay, George, fair enough. Okay, I'll try to do it within the free band model and see whether it is. And that's essentially the thing. And I will have opportunity to confront with George Savatsky again, because they are organizing this Materials and Mechanisms of Superconductivity conference next year in Vancouver in Canada.
Okay, thank you very much.
Thank you, Romek.
Thank you, Roman. Thank you, speaker. Please, next comments or questions, please go on.
Darek powinien się coś odezwać, mimo że on jeszcze ciężki fermion jest.
Okay, so maybe I stop recording.